The A3C algorithm, which is not this is my improvement on A3C, has two output functions, one that predicts policy, one that predicts utility. It builds on top of the actor-critic model that we talked about before, but it uses one model to do them both. And the idea is mapping from the input image to policy and mapping from the input image to value. They're different problems, but a lot of the internal structures that it needs to learn might have correlations, and therefore it turns out the model actually does do better. So yeah, there is some value in using one model to do both problems. Okay. Well, I decided to take that one step further. So the A3C algorithm is what's called a model-free reinforcement learner. And the idea of a model-free reinforcement learner is it doesn't utilize a model of dynamics. Remember assignment 6, we built a transition function that predicts if you do this action, here's the state we'll transition to. That's a model of dynamics. If you have a model that learns if this, then that, that makes reinforcement learning work better. But so far, people haven't figured out how to make it Q-learning and models work effectively together in a way that, that's only partly true. It's largely not true. Here's my point. I was trying to come up with a way to fuse dynamical system models with Q-learning. And it occurred to me, hey, what if I could use the same model to do both of them? Then I could do transfer learning. The problem is, you usually predict, let's see. Well, to make a long story short, I just stuck an extra head on this model and said, hey, this also predicts the anticipated observations. And therefore, this whole model is going to learn to anticipate not only what action to do, how good it's going to be, but what I expect to see when I do that. Okay. This whole model has never been tested. This is just a diagram that I'm proposing to build if they give me a bunch of money. They probably won't. But that's kind of what we do as professors, is spend a lot of time coming up with ideas and writing reports about them and begging the NSF to give us money. And if they do, then I'll hire grad students and make them go build this model. And hopefully it will work, and maybe it won't. And if it does work, then science has been advanced. Now, obviously, it wouldn't be enough to just make that one contribution. So let me show you some more ideas that I threw into this model. You see here I have a layer called spectral decomposition, and I'm feeding this into a whole bunch of different layers at various levels in my neural network. What do you suppose that is? So, you seen this diagram before? It should look a whole lot like what you did in assignment 5, one of those assignments. And this one on the right is what it gets with a different data set. Okay, well, what I'm claiming here is, hey, if we have the access to a bunch of sinusoidal units that are sinusoids of different frequencies of time, that's really useful for predicting how dynamical things change over time, right? Well, if I'm going to be building a model here that needs to anticipate what are the effects, if I do this action, what will be its possible effects, what will be the utility of performing that action, and because things are changing over time, it occurred to me that, hey, if I take time and I run it through a bunch of sinusoidal units, which does a spectral decomposition, and feed that into my neural network, wouldn't that make it very useful for predicting the future? Don't know if it will, but in my proposal, I spent a lot of time talking about how this is certainly going to make it just work really awesomely. And if it does, then that would be science advanced. So there, I proposed that. Now, notice I'm feeding all of my low frequency values into the deeper weights, and I'm feeding my high frequency values into the more output layer units of the neural network. Here's my idea behind that. how can I describe that? Has anybody started reading that On Intelligence book yet? Cool book, isn't it? Okay, well, in there, he makes this big claim about how the cerebral cortex breaks things down such that in the deeper layers, you're following low frequency patterns, and in the more output level layers, you're tending to recognize very fine-grained, high-frequency patterns. So in order to try to promote the neural network to break things apart in a way that mirrors the cerebral cortex, according to that book, I thought, hey, if I feed the frequencies into these varying layers, then maybe that will help it learn things in the manner more analogous with the way the brain seems to do it. So another idea I threw into this. Here you see I have something called spatiotemporal attention. Remember assignment 6 where we just feed the x and y coordinates of the image of what we're looking at into the model, and that allows us to predict one pixel at a time? And that also allows us to put the image on the output end rather than the input end. Well, that's what I'm doing here. If I feed those coordinates into my model, and then this only has to predict a single pixel, that allows this thing to learn without having to process all the pixels in an image. So I'm throwing in another of my tricks there. Finally, I have a small recurrent little portion here. This is basically my transition function, which is the same thing as we did in assignment 6. And what you're looking at here is, this is my idea for something I want to build that, in theory, should become highly intelligent and capable of learning to solve really hard problems. And I propose to throw this at the problem of teaching robots to imitate humans. And let's see. And here's a picture of some robots, so give me some money. There you go. That's about what that comes down to. Anybody ever written a proposal before? Probably something we should talk about in a graduate level class, just so you're aware of it. This is a proposal. Notice it's about 15 pages long, of very dense technical writing. I have 135 references in this particular one. It took me months and months and months to write. And there's a bunch of technical stuff you have to put in there. It was a lot of work, and is probably going to get rejected. This is the life of a professor, writing lots of these. It's kind of your full-time job. So if you want to forge on and get a PhD and work at a university, you too can write proposals and come up with crazy research ideas and beg people for money, and maybe they will and maybe they won't. And hey, you guys recognize this, right? Do you know what this is? This is what you did in assignment 6, except I injected noise into it as well. So you were reconstructing the path through which that crane followed. This is the path through which the crane followed with transition noise and observation noise. And this is the reconstruction of it. And you see how it's not quite the same, but still the same colors are in the same regions of the graph. And this shows I was able to reconstruct an internal state from observations. And I'm using that to validate the idea that, hey, maybe this spatiotemporal pixel location will enable me to still learn latent state based on a single pixel of anticipated observations. Here's my poster. That looks like a crazy big scary poster, doesn't it? Okay, this is a paper I published, when was it? 2 or 3 years ago? This is about cognitive architecture. Do you remember what a cognitive architecture is? You guys just kind of dead today? I got a few nods. Okay. Cognitive architecture is a way of putting together a whole bunch of neural nets or other learning models to try to build a great big brain. And if anybody's interested, hey, I have here this poster, and you can sit there studying it and understand how I think some things are going to fit together. This be interesting to talk about for a bit? Okay. Here is my diagram of a software agent. I think you'll agree with me that this is pretty darn standard. The idea is, here's the world. The world provides observations which feed into your agent. Your agent thinks about it for a long time. The artificial brain, of course, is the hardest component to produce. It selects some actions or some signals to send off to your muscles, and that affects the world. Isn't this basically the cycle that even you as a human follow when operating in the real world? Okay. But now the question you're all dying to know is, how does the artificial brain work, right? And so this I expand through my light into this diagram. It looks like a beam of light, doesn't it? What I was trying to say is, wow, that's a little bit big. See how that expands into this? Okay. In my view, and by the way, there's nothing right or correct about this architecture. This architecture is just the way I like to put things together. An artificial brain, again, takes observations as input and produces actions as output, right? I'd break down intelligence into two major components: learning and decision making. And you can kind of see why, right? Basically, if everything you see enables you to learn, then you become smart. Once you're smart, you decide what to do and use deciding what you do to pick your actions, and now you're operating in the real world. You think that's a reasonable breakdown? Okay. Well, let's take our learning system here, where a learning system is some model that can take observations and can learn to understand things. And let's look at how I thought that one should work. Here's my learning system. Okay, think deeply about assignment 6, where we built that crane system. It had a transition model, had an observation function. Do you see that right here? I'm claiming that's kind of enough to build a universal learning system. And I think at one point I proved that to you, that assuming there is state in the universe, a deep neural network is sufficient to model the transitions of state, is it not? And a deep neural network, given the correct state, is sufficient to predict whatever observations you might make. Therefore, I claim this model is enough that it can represent or understand or come to fit any universe you throw at it. Can you see how that might be the case? Yeah?
Isn't there some theorem, like no free lunch, that doesn't can't do that?
Yeah. So the no free lunch theorem actually says, that's an interesting to talk about. Let's see how much time I have. 6 minutes. Yeah, I'm going to break here and talk about the no free lunch theorem. I know I'm all over the place. That's okay. We're going to end this class on a big pile of stuff dumped on you, and then that'll be the end. No free lunch. Also, the National Football League. In machine learning, NFL means no free lunch. The idea of the no free lunch theorem is this. Here are some points. What are possible functions that go through these set of points? One of them is pretend that goes through these points. I can't draw a straight line with my mouse. Pretend that function goes through those points. Okay? What does this model predict for right there? Well, it predicts right there. Right? But how many possible functions are there that go through these points? Well, there's this one, and 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 there's this one. That's not a function, just kidding. There's this one, and there's this one. Okay. Imagine if we enumerated all possible functions that fit to the data very nicely, but then do whatever the heck we want them to do. Do you see that basically there's an infinite number of functions over here that can do whatever the heck? And you also see that these functions have absolutely no relationship to the training points. Imagine that this thing that we're looking at is assignment 5. Remember assignment 5 we fit training data is everything on the left, predictions everything on the right. Well, if our training data is not predictive of the future, if the training data is not representative of what you're trying to predict, can you predict anything? The answer is no. And here's how David Wolpert, who wrote the no free lunch theorem paper, he now works at NASA. I think he did at the time he wrote it. I met him, by the way. He came and did a colloquium at my university. Not that anybody cares. Here's how he proved it. So here's a function, right? But you could represent a function as an array. So imagine a box here, box there, and let's do a target. Well, and let's just do binary right now because it's easy. If we have the vector 0, 0, 0, and it could map to a 0, and we have the function 0, 0, 1, and this maps to a 0, we'll say, we could run through and enumerate all possible binary combinations of the inputs. Could we not? Well, we could also run through and map all possible binary combinations of the outputs. And we could pick some subset of those inputs and corresponding outputs, and we could call it a problem to learn, where you try to learn from these inputs to those outputs. But do you see that on average, the outputs have nothing to do with the inputs? Okay, well, he demonstrated empirically by systematically running through all possible combinations that, in fact, well, see, if this is your training data, but then your test data actually looks like this, you're going to do very badly, right? Let's see, how can I explain that? I actually like it in continuous space better. I think this is easier to explain. The long story is, if all possible functions are equally likely, and this is the great assumption of the no free lunch theorem, if all functions are equally likely, then it turns out there's absolutely no way to make useful predictions. And he did it by using an array to represent the function itself. Because you can use, if you discretize this, essentially an array would be a discretization of it, right? Okay, well, the no free lunch theorem works if and only if this assumption is correct. Now, here's the big question, is that assumption correct? Well, I can prove it's not in reverse. Then learning is futile. I claim learning is not futile. Here's how I know learning is not futile. Because I used to be dumber than I am now. I claim learning is not futile because, hey, we built a university and we wouldn't have done that if there wasn't a point. I claim learning is not futile because I'm talking. I learned that when I was young, right? So learning is not futile. Therefore, not all functions are equally likely. So what's the point of the no free lunch theorem? A lot of people come out and say that its purpose is that you can't learn, that learning is futile. Well, it's true, that was the conclusion, but that was the conclusion based on this ridiculous, absurd assumption. And so what we can actually conclude is, in the real world, having a bias, having a preconception of which functions are more likely than others is really, really important to learning. And so the correct interpretation of no free lunch theorem basically says, don't consider all hypotheses equally likely. Don't assume that anything as possible, rather try to keep things simple. Does that make sense? Nobody has yet sorted out the world's best bias, but there's one that's pretty much generally accepted called Occam's razor. You've certainly heard of that, right? Occam's razor says the simplest model that explains all of the known data is probably the best one. So for example, if my undo history ran out. Oh, I'm over time. Here's my deal. Occam's razor basically says this one's probably the right one. It's probably this one, right? Why? Because that's the simplest model that went through all of these points. All these other ones are kind of doing crazy stuff, and the simpler models are more likely to be correct. Okay. The no-free lunch theorem just proves you need some kind of a bias. Occam's razor is a good one. There are others. Anyway, I'm out of time, so I got to let you go. Thanks for coming.